Hello, welcome again. So in this class, we are going to be looking at time response of first order systems and second order systems in more detail. Today, we are going to look at the time response of first order systems. First order systems occur very commonly in nature. They occur whenever the governing equation is a first order ordinary differential equation for the system. So if we have an ordinary differential equation of this form, R is the input variable, Y is the output variable. Finding the transfer function, we will express Laplace of the output variable divided by the Laplace of the input variable, taking zero initial conditions. We end up getting the transfer function as this. So notice over here that for the transfer function, we do not have any zero, and we have one pole at s is equal to minus a location. So this is a first order transfer function. In nature, first order transfer functions happen whenever your system response is not oscillatory. So, for example, if you think about response of a thermocouple or a thermometer, the level of mercury increases to the second set value and then reaches a certain steady state value. So that is a typical first order system response. Even when we look at the mass spring damper systems, if we have very high damping, we are not going to see any oscillatory response. So the output response is dominated by the first order characteristics. So if you look at response of motors, for example, you switch on the button for the motor, you switch a motor on, it increases to a certain steady state speed value and settles down over there. So that is a response which is dominated by the first order characteristics. This happens in many appliances, for example, in your ceiling fans, in your food processor, and so on. So first order response is quite important. First order and second order response together are quite important response to study. This expression, so over here, we have expressed the transfer function in a way we can easily tell that there is no zero and there is one pole at s is equal to minus a. So this is called the pole zero form. So remember that earlier we have expressed transfer functions. We have expressed the transfer functions often as some polynomial of numerator, and we used a form like so we used a form in which we factorize the zeros and poles, and we can tell that the zeros are located at z1, z2, and so on. Poles are located at p1, p2, and so on. So this form of a transfer function is referred as a pole zero form. Alternatively, we can also express the transfer function in a form which is referred as a time constant form. So in this case, we can rearrange the terms to write the transfer function as k over ts plus 1. And if we compare it with the form above, the pole zero form, we find that the time constant is nothing but 1 over a, and the k, the constant in the numerator, is b divided by a. So this is referred as a time constant form because it describes some important characteristics of the system. About it specifically, it describes how fast the system is going to respond, and it also describes where the system is, first order system is going to settle down. So here k is referred as a system gain, and the time constant is basically tau. We can see, you can, I'll let you do it yourself. You can try solving this differential equation. You can also solve this differential equation using the Laplace transform and inverse Laplace transform. So the Laplace transform is already, the transfer function is given to you. You can assume that Rs is a step function. So you can get y is equal to transfer function times Rs, where Rs is a step function, so its Laplace transform will be 1 over S. If you take the inverse Laplace transform, you will see that the step response, the unit step, it's not so the unit step response in this case is going to be equal to k into 1 minus e to the power minus t over tau. So you can check it yourself. Also notice that the pole zero map, which is basically just showing where all the poles and zeros are located. So there is no zero, but there is one pole at negative a. So it's quite a simple one. So it is the pole zero map is at negative a, which is also equal to negative 1 over time constant. So we can see, looking at this step response, we can see that we can see that as time t tends towards infinity, this value is going to approach. So the exponential term is going to approach to 0. So inside the bracket will approach to 1. So the overall steady state value of the output will approach k, which is shown over here. So you can see that when we apply a step, so in this case, k is assumed to be 2. So we end up getting a response which increases and then settles down at the value of k, which is equal to 2 in this case. Furthermore, we can see that if the value of tau is large, then it will take a long time to settle down. Alternatively, vice versa, if the value of tau is small, then the response will quickly approach the steady state value and settle down close to it. So this kind of a response is a typical response for the first order system. But we can see that at the value, so you have also done this in your previous classes. You have also done it in your previous math classes, as well as you may have solved it in some other problems. We can see that at time, if we replace time t, with tau, we end up getting the response y is equal to k into 1 minus e to the power minus 1, which basically equates to 0.63 of k. So basically, at time is equal to time constant, the response is 63% of its steady state value. If we draw a tangent for the response curve at time t is equal to 0, we'll also find out that this tangent intersects with the steady state value of a horizontal line at steady state value at time t is equal to tau. We have learned that the steady state, there are a few important characteristics. We learned about the time response characteristics in the last few lectures. So we looked at the settling time. So settling time we saw was a time when the settling time was a time, 2% settling time was a time when the response was within 2% of the steady state value. So in this case, since the response is basically increasing monotonically, so whenever it reaches within the 2% band, then it stays within it. So we can substitute for 2% settling time, we can substitute y settling time, or y at, we can say y at 2% settling time is equal to 0.98 of the steady state value, which is k. So if we substitute this in the equation on the top, we end up getting that the time is almost equal to 4 times the time constant. So after 4 times the time constant, we are roughly within the 2% of the steady state value. Also, we discussed the rise time. So we discussed that the rise time for a monotonically increasing response is when the response goes from 10%, 0.1 k to 0.9 k. So we looked at the rise time for monotonically increasing response to be from 10% to the 90% of the settling time. So this can be found similarly by substituting in the equation. This is approximately equal to 2.2 times the time constant. Please note that rise time is defined differently for the oscillatory response. So if the response was oscillatory, then the rise time is basically defined as the time it takes to go from 0% to 100% of the steady state value. So whenever it reaches the steady state value for the very first time, so this will be the rise time for the oscillatory response. So this is referred as a rise time for the oscillatory response. So this, I'll wrap up the flipped lecture over here. We'll look at the example in the classroom. Thank you.